Today, we will be exploring how we can provide universal access to Australia's ocean pools, a spectacular topography where land meets water. People's experience with objects, services, and spaces are dependent on their ability to process visual and tactile information.
Our project investigates how patterns of erosion can inform people with different sets of abilities, particularly the vision impaired and blind, through tactile sensory interactions to choreograph a meaningful understanding and awareness of the space around them.
These patterns of erosion have then been developed into a suite of navigation tools that provide the vision impaired with an in-depth understanding of the topography around them. An understanding of the surroundings from a macro to micro level allows the vision impaired to traverse with a greater degree of safety.
Our goal of providing universal access to the vision impaired is in response to Sustainable Development Goal 10, to empower and promote the social inclusion of all irrespective of disability, SDG 11 to provide universal access for people with disabilities, and SDG 15 to protect and restore ecosystems.
We began with a geological exercise to create a catalogue of the different patterns of erosion, rock types and formations that were evident at Malabar. Our cataloguing exercise was then supplemented with a study of the history and coastal geomorphology of rock formations. We utilized a series of drone capture, photography, scanning, and photogrammetry in this process.
The creation of topography through the principles of geology can reveal the constantly changing region between the ocean and the land. This can be defined as coastal geomorphology, a discipline which is primarily concerned with the coastal weathering processes of erosion and deposition of rock and sediments by wind and water.
By mapping the patterns of erosion at Malabar, we observed several different phenomena. For example, we see the pattern of pitting, linear crevices, and smooth areas. We were most interested in the pitting and linear crevices and the potential of these patterns to be used as a mechanism for wayfinding to provide enhanced user experiences and inclusion.
Through the pattern structure of circular pitting onto the rock face, we can observe changes in density and gradient conditions among clusters. These patterns are not arbitrary and are formed through a relationship of salty deposit residue that have caused erosion and resulted in a pitted pattern structure on the rock face over time. Tactile plates have been created through a process of photogrammetry, post-processing, and 3D printing. This provides the vision impaired with a physical interpretation of the environment around the ocean pool.
In navigating the tactile plate, the principle of higher density to indicate a condition such as danger can form a useful strategy for spatial mapping of the ground plane.
Linear cracks and crevices in the landscape have also been seen to inform the pattern language of the rock faces, with lines dissecting in multiple directions, but also with a higher concentration towards the water's edge. These lines can inform boundaries of navigation and can assist as directional markers when needed.
Both examples form a mechanism to move through space, in which tactile pattern structures of density and linear boundary movement make the site more accessible. These gradient conditions indicate how the body can connect to the space and begins to form safe navigation passages by indicating a condition ahead.
We now understand the logic behind the variations within these erosion patterns, but we need to extract the patterns themselves from the rock face to manipulate them as required. In both the pitted and linear versions, we begin to see a clear geometric language appear.
In these examples, we can see that an increase in density of pitting typically indicated a closer proximity to the water's edge and an increased sense of danger.
From this geometric study, we began to create our own pattern language, working to relay the experience of touching these surfaces, whilst clearly articulating the changes in density which allows us to utilize these patterns to aid the visually impaired.
Through a combination of grasshopper evolution and geometry optimization, we were able to recreate and simplify these patterns of erosion in a way that allows us to easily adjust and modify them to suit the required purpose and to make them more easily understandable by touch.
Our patterns were then translated once again into a form that ensured the robotic arm could both understand and recreate the desired three-dimensional form. We tested our variations of both the pitted and linear patterns as well as an inverted version of the linear pattern. From a user perspective, tactile plates can begin to describe specific rock formations and reveal information of the tactile experiences through simulated examples of what can be expected at a particular site. The plates also assist in introducing the rule of density equals a condition ahead to establish a new language by which the site can be navigated.
An underlying idea which has been apparent throughout our explorations is the slow yet constant change which these rock formations are undergoing. Our pattern analysis and understanding can be used to predict what these formations may look like in the future, aligning with SDG 15, which aims to protect and restore ecosystems like this.
This constant cycle of erosion and weathering, which causes the changes in the rock, slowly wears down the surface to lower depths. This idea of patterns in 3 dimensions was briefly tested in this model, which overlays the pitted pattern previously used but exaggerates the 3rd dimension. So, through all our pattern research and investigation, how can we assist the vision impaired in traversing a typically inaccessible site? To do this, we aim to provide a suite of navigation boards that are specifically designed for the vision impaired.
The boards are designed to provide an in-depth understanding of the site from macro to micro scale. At high level, the orientation object assists the vision impaired with the overall layout of the site.
Through hybrid insertions of distinct 1, 2, and 3 markers into the object, we are able to provide tactile representations of the different regions across the site. These numeric markers correspond to the family of tactile boards available.
The family of boards provide tactile representations of the topography found at the corresponding locations at Malabar. Distinct pitted and linear crevice features can be identified on these boards through a tactile reading by people who are vision impaired.
At a micro level, these pitted and linear features are described through the simplified milled board patterns, which provide an understanding of the relationship between the density, size, and spread of features.
This level of understanding aims to provide a coherent relationship between the tactile features and the level of caution one should take when traversing such topography, by indicating, for example, the proximity to the sea line through the density of features.
To accompany this, vision impaired users are provided with thumbstick guides to refer to while traversing the topography. The guides provide a representation of the pattern density and corresponding level of danger. The information presented through these tactile plates form a pilot study for the potential of navigation boards that assist the vision impaired to traverse the ocean pool environment.
Today we have explored how patterns of erosion found at Malabar can be utilized as a mechanism of navigation for the vision impaired to traverse the topography. This aligns with our targeted sustainability development goals to empower and to provide universal access to all, irrespective of their ability. We envision that the pattern language developed could be utilized as a mechanism of safe navigation across the ocean pool environment in Australia.